Welcome to today's webinar. The topic today is Grasshopper RFEM 6 modeling cross-laminated timber structure. In this webinar, we will show you the workflow of the interface between Grasshopper and RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the content of the website, the German and English webinars, newsletters, customer projects, and so on. I will be the moderator today, and I will answer your questions together with Paul Sivolgin. The presentation will be done by Lukas Sühnel. Lukas is responsible for product engineering and customer support. For instance, for the development of the interfaces between RFEM, RSTAB, and other programs. Also, Paul is responsible for the interfaces in RFEM 6 and RSTAB 9. Okay, then I switch off my webcam that you can see the full screen. Some words how you can ask questions. You can click on that question mark above. Then you can enter your question here in that field, press send, and we will receive your question and we will answer you. Okay, that should be also all from my side. I hand over to Lukas. Lukas, it's your turn.
Thank you very much, Andreas, for the introduction. I will continue with the content of today's webinar. In the beginning, I would like to give you an overview of the latest developments in a short PowerPoint presentation. And in the second chapter of today's webinar, I will do a live demonstration of the interface or the Dlubal Grasshopper link. This time I will start from scratch. That means I will create the Grasshopper algorithm and then the connection to RFEM 6 with our Dlubal plugin. So let's start with the latest developments in that area. By the way, most of those implementations came from customer wishes. So in case you are missing something in the plugin, please feel free to contact us. The first little feature that we implemented were the scissor hinges in our member hinge component. Additionally, we developed 3 new components for the nodal, line, and surface FE mesh refinements. So now you can control finite element mesh on those objects. In the upcoming update of the plugin, we will also implement a new component which will allow you to control the global FE mesh setting. Last feature on this sheet is are the definition nodes inside quadrangle surfaces. As you know, quadrangle surfaces can have 3, 4, or even more boundary lines. The shape of the surface will, however, be defined by the 4 definition nodes, and those can be defined in the surface component now. We also developed new components for the surface contact. The surface contact is, let's say, or has been introduced to RFEM 6 as a new feature. You don't have that in RFEM 5. And it is, let's say, an easier to handle alternative for surface contact solids. We also extended the member and surface components with additional inputs for the stress strain analysis, timber, and aluminum design add-on. How you can control these add-ons I will show afterwards. I think the key feature is here the template functionality that we implemented a while ago into our export component. And the last feature that I will show here in the PowerPoint presentation is the extension of the thickness component for variable thickness types and multi-layer surfaces. This obviously will be a topic of today's live demonstration. The last feature that I would like to show here is actually related to the installation process of Rhino. So let me show you Rhino 8 in a second here. In the past, the plugin could be installed via a specific folder in the RFEM 6 program folder. We changed it. Everyone can install the plugin now via the Rhino package manager. So if you go into Rhino and you call up the package manager, you can search for Dlubal here, and you can see the Dlubal plugin, and here you have various versions of the plugin. An important information for you: in case you're using Rhino 7, you should use the versions with the number 7 in advance or in the front. And in case of Rhino 8, use the versions with the version number starting with the 8. Yeah. For today's webinar, I'm using, let's say, an internal version. Anyway, you can do the exact same algorithm in the current customer version of the plugin. All right, then let's switch to the second chapter of today's webinar, the live demonstration. To give you a feeling for what I'm doing in Grasshopper, I would like to show you the final structure first in RFEM, and then hop right into Rhino 8. So that's the CLT structure that I would like to model. It should represent like a bus or train station, where you can wait for your train or for the bus, and you're protected against rain and wind and so on. So you have here these CLT wall, slab and wall elements, and inside some additional timber beams that support the roof, and on the front some openings to go to the train, and on the side some windows to let's see if the train or the bus is coming. Obviously a made up example, but it serves the purpose of today's webinar. I would like to show you the workflow and some new components. What do we have here as well? We have some line supports on the bottom, and additionally some line hinges, because CLT panels are usually connected hinged. So we need the line hinges as a tool here to have the proper force transfer. That's also the most tricky part of this whole algorithm. I will explain it obviously, of course, afterwards. And apart from that, we have, of course, our new layer thickness types in here, in which we then define the layers individually. All right. That should be it as a rough introduction of the structure. Let's go right into Rhino 8, and here I will do it in a way that I put Rhino to the left and a Grasshopper to the right in a second. One more little overview for you, what I will do now or in the next hour roundabout. I will model or create this algorithm here. We start with the Grasshopper algorithm, where I model the roof of the structure, then the walls with the arc, the wall with the window, then some data management, copying and so on of stuff, collecting my objects, the surfaces, the lines that I will use again afterwards, and then the connection to RFEM via our Dlubal plugin. I will create materials, sections and members, thicknesses and surfaces, and last but not least, lines, line hinges and line supports. All of those components then will be connected with our export component, and we get the structure in RFEM 6. All right, so let's create a new file in Grasshopper, move it to the right hand side of the screen, and start with the modeling. As I said, I would like to begin with the Grasshopper algorithm, so I need a plan how to model that, and I will start with the roof. The roof was curved, and therefore I need some kind of a curve with the interpolate component. The interpolate component requires the nodes. You can see it basically on this little icon here. You need to define the nodes and then it will interpolate a line or a curve. And therefore I need 3 nodes and I use the construct point component for that. The coordinates of those nodes should be defined with MD sliders. MD slider. This MD slider properties will be changed a bit, so from 0 to 10. So with this slider I can define basically a node, a coordinate x, y, z. Z, however, is always 0 here, so I change x and y coordinates by moving this little dot. Now my curve will be in the xz plane, therefore I need to deconstruct the node that I get here. So I deconstruct the node and I construct it, or I build it again just using different coordinates. So x should remain as the x coordinate. The y coordinate, which I can modify here, should be the z coordinate. So you can see now, actually that's already the second node, my bad. The first node should be at 0, 0, 0. So that's the first node here in the center of origin. The second node, which I can modify now with the MT slider. And the third node should also be modified via an MT slider. So same logic. Y should be set. And now I can define this arc. Let's pick some proper coordinates. And now I can connect it to my interpolate component and I have a curve. So that could be the shape of my structure, for example. Alright, now I need a surface, so I can simply extrude this curve into the y direction. And yeah, I want to define a distance via a slider, so I define a slider from 1 to 5, for example, using the metric units here in my head. So now I can extrude this line into a surface. Alright, that's basically it. That's already the first part of my little algorithm. And I group it, and for a better understanding I can give it a little name. So that's my roof surface, for example. Okay. Alright, so second part is the wall on the front. Let me show it again in RFEM so you can follow easier. I want to create this wall now with the arc-like opening. So what I need for that is I need this line here and I want to extrude it into the Z direction. To get access to this line, I will deconstruct that surface. Therefore I have here the deconstruct brep command. I link it to my surface. Now I have here the faces, the edges and the definition nodes, and I need just one of these edges, so I take a list item component, connect it here, then define the little slider to select the line from that list. Let's see which it is. Index 0 is the one on the end, on the bottom. Index 1 is this arc. Index 2 is the line that I need. Alright, so I have this single line in this component now, and now I simply extrude it again in the Z direction. And we can already see it is the wrong direction. So I probably need to multiply it by -1 or -1. And the coordinate itself comes from my arc or my curve that I defined in the beginning. It's the Z component or Z coordinate of that node. So obviously the Y coordinate here and multiplied by -1. So we make a little multiplication component. And then it always has the right height. Yeah, so even if I play with my MD slider, the wall always gets the right height at the end of the day. All right, that's the first part. Now I need the opening. For the opening, I also use the interpolate component again, and I need again 3 nodes. All right. Yeah, sorting can be done at the end of the day. All right. So where should the first node be? Basically, all of the nodes have the same X location as the wall or the end point of my curve. So the X location or the X coordinate is always the coordinate from the last point of my curve. And now I need to modify the Y and the Z coordinates. The first node should only move slightly in Y direction, so I make a small number slider, and I want to have like floating points, so I change the type of it and connect it to the Y coordinate. So this distance that I define here via this node is basically the length of my wall support on the bottom. The second point should be in the center. Center basically means the dimension of the extrusion divided by 2. So divide by 2. Link it to the length of the extrusion, and that's my Y coordinate for the center point. And I need a number slider to modify the Z coordinate. All right. Maybe also where floating points, so like that. And the last point is again on Z on the bottom of the surface, and it should have the same distance as the first point. So again, I just do a little subtraction. I subtract the extrusion length from my required support length. That's the Y coordinate. So whenever I change the length of the support, it will change on both sides. All right, these are my 3 definition nodes for my curve. And now we can see it. The next step is, let's say, like a trim command. I would like to cut out this part of the arc from the rest of the surface. I can do that with the component split brep. The base surface is this one, and the so-called cutting shape is a surface. So I need to extrude my arc again into X direction to get a surface for it. So actually extrude first, extrude in X direction. Yeah, just any surface. And now I can use it to cut the original shape. I get here 2 surfaces now. I just need one of them. So again, a list command to pick one of those indexes. And a little slider to select the right one. So index 0 is the, let's say, the surface of the opening. So index 1 is the remaining surface, and this one I want to keep. So let me hide some of the other objects to see the result of my little algorithm. That's the remaining surface. That's the one I need for later. So I already finished the second part here. Again, I could give it a name. Arc, surface, whatever. Just that I can easily understand what I'm doing even a couple of weeks later here. And now the last surface is the surface in the front. To create that, I would like to use the edge surface component. I only have to define the boundary lines. One of my boundary lines is, of course, my arc that I defined in the beginning, yeah, like from the roof, this, or not arc, but curve. And the second curve for my surface should be this side line of my front surface. So again, I deconstruct this surface here in the front, and I select, or I try to select this line here on the side. Again with the list item component. Let's connect a slider to it, and now let's go through these lines to see which of them it is. Oh, sorry. The edge lines, of course, obviously. So that's the other side. Oh, come on. Yeah, now I have it already indexed number 2. It is, yeah, that's the line I need. So I connect it again to that surface component, and I already get the final shape. So far so good. Now I need to cut out a rectangular hole in here. Same logic as before. I will create the, let's say, the rectangle in this case by 2 points. Yeah, the 2 points are A and B. And then I extrude the rectangle and then cut it again from the original surface. These 2 definition nodes of the rectangle can or shall be defined again via an MD slider. So I just copy some of those things here, copy, paste, and I will reuse it down here. This time, yeah, no, actually that's already okay. I can connect them as definition nodes for my rectangle. The rectangle can be placed in any plane, as you can imagine. So I can define the plane by setting it here graphically, or in the Rhino lock, or however you call this area here on top. And I would like to have the rectangle in this ZX plane. Okay, yeah, that's now on the right plane. Let's set some proper coordinates for the rectangle. So maybe that's the size of the window that I would like to have, and now I have my rectangle here. Again, I extrude it. Into the Y direction. And now I can use the split command again, split brep, to cut out a hole. Let me copy the list item that I defined on top here. Again, I want to keep only one of those surfaces, and this time I think it is the index 0. Exactly, yeah. So let's hide some stuff to see the result of our work here. Yeah, that's the remaining surface with the opening, the rectangle opening. All right, that's already the basic geometry that I need. And now I can copy this stuff. Sidewall, let's say. Okay. Now let's copy the surfaces. That can be done with the move command or move component. And which objects do I want to copy? Of course, my roof surface and my front surfaces or front surface. And the default is set, as you can see. Yeah, it's copying it in the vertical direction, which is not correct. I want to copy them in the Y direction. And I want to copy them multiple times. For copying something multiple times, you can combine a move command with the series component. And as a step, I would like to use the extrusion length, of course, yeah, to have them placed next to each other. Now I can control the amount of copies with a small slider, let's say 4 copies. All right. That's a big part of the structure. Now I only have to copy the front surface to the end. So I use another move command for that. And I copy this surface. Of course, not multiple times. I only want to have it one time. And then the end and the distance for this is actually a little multiplication. We simply multiply the extrusion length with the amount of copies. And that's the length that we need to copy it from the front to the end. Okay. So far so good. The geometry is done. What I need now is I need a little bit of data management, because afterwards, thinking of the RFEM6 connection, I need a collection of lines. I need the collection of lines on the bottom, all of those down here, because on those lines I would like to assign a line support. And I can use these lines in my line support component to export it to RFEM6 afterwards. Additionally, I need these 3 internal curves, because I want to assign a member or a cross section to them. And maybe also a collection of all of the surfaces that I have. So maybe let's start with the curves for the beams. How do I get those? They are basically inside that component. This component contains all the surfaces from the roof and from the front. Now, if we take a look at the data in that component, we see that it has 2 groups. Let's call it 1. 4 open extrusions. These are my roof surfaces, and in the second group, my wall surfaces. So what I can do here is I can explode this tree and get each group on, or get each branch of my tree, or get access to each of these branches. First branch, second branch. So, and the first branch, as I said, contains the surfaces of the roof, and I can deconstruct them again. So you can see it here again. Those are the surfaces, and of course the boundary lines and so on. And now I would like to select only these internal curves. So basically just one of those lines per surface. So I need again a list item component from my edges, and let's see which of the index numbers it will be. The index 0 is are the lines on the bottom. I need that maybe later for my line supports. I'm looking for the roof curves. And index number 1 is the one that I need. It contains these curves. However, it contains 4 and not just the 3 that I need. So what I can do now is I can, let's say, get rid of the last index from that list. Currently, it is not a list. It is, let's say, a tree. On each branch of the tree, I have 1 curve, but I can make a list out of it by flattening this tree. And now I remove the last index. And it can be done by using cull index component. And the last index can be defined by a panel with the -1 value. And the remaining lines are the ones that I need for my beams. So let me collect that in an additional component so I can easily reuse it afterwards. Maybe again a little comment here. Curves for beams. Okay. Now, second part should be the curves for my line supports. We already saw it in that component. Here I can select, let's say, the curves on the bottom of those roof surfaces. It was the index 0, so that's already one part for my line supports. And the other bottom lines are included in the wall surfaces. So basically I can copy this part, connect it to my surfaces here in the front, and now look for the index number of those walls. Which of those lines are the ones on the bottom? So I scroll through that. Index number 1, as we can see. And now my slider is not long enough, but I can tell you that it's the index number 5. So I need index 1 and index 5. So I create a little list, 1, 5, and connect it to that component. So this list item gives me now the lines from my, or 2 lines, the index 1 and the index 5, and yeah, we can hopefully see it, or you can hopefully see it, that it's the line on the bottom, on the right and on the left side. Now I need the bottom line from the side surfaces. Yeah, same procedure. I copy again this part. I connect it to my, well, actually I need 2 surfaces. The front surface, which is down here, and also the copied surface from the back. Yeah, and from both surfaces I need 1 line. Yeah, we can already see it is the index 0. So in here I have now 2 lines, and yeah, these are now the lines that I need. I can collect all of them in one component again. So just connect them to the curve component, and that component contains now all the bottom lines for my line supports. So again, give it a little description. Line support, lines. Okay. And yeah, then I also collect my surfaces in a surface component, which I think most of them are contained in that component. Yeah, where I copied them. And additionally, I have the front wall and the wall on the back, which is in here. So this surface component contains now all surfaces. All right. So far, so good. Now, next part is the connection to RFEM 6. So therefore I need my Dlubal plugin. Let me increase Grasshopper for a second. The Dlubal plugin will show up after you install it, obviously, and it is divided in 3 parts. We have the model data group, which contains most of the basic objects, nodes, lines, members, surfaces, materials, sections, also components for solids, for thicknesses, supports. I think most of the stuff that you need is implemented in here. We have another group which is called loads. In here you have components to create load cases, load combinations, but also the loads, nodal loads, line loads, member loads, surface loads, but also imperfections, in case you want to assign them as well. And the last group contains general components, for example the export component, import component, a component that allows you to run the calculation of RFEM 6 via Grasshopper, or other components. For example, that's, as I said, I use in internal version the global mesh setting component. All right, how do we start? I think RFEM gives us a nice hint here. The data navigator in RFEM shows us the basic objects and then specific objects, types for nodes. And it's kind of the logic that you use when you're defining your structure. First you define materials, then the sections and the thicknesses. Then you continue maybe with members and with surfaces and solids and so on. And the same logic we use in Grasshopper. I start with the definition of my materials and sections. So The material component can be found here. And a material can be defined by the index number that it should get in RFEM 6 and the name. The name ideally equals the name of this table down here. So you can define your name in or your material in RFEM and copy the name. By the way, to get the full name, you can check the program options and see if you have the full section and full material description activated in here. If you do not have this option activated, you only see GL22H. The code related part of the name will not be shown. But to have a clear assignment of a material, you need also the standard. Yeah. So we can copy that name and paste it into Grasshopper. Alternatively, if you had previous projects and you already did this, you already defined materials and sections, you maybe already created a little library, yeah, your own little library of materials and sections that you use again and again. And that's what I did. I defined here a value list, and I put my own information into that value list. Yeah, you can do it by editing this value list and then just insert the names into it. Yeah, that's the name that it shows here, and then that's the name which is behind that little description. It's identically for me here, but you can simply copy these things here. Yeah, then you select the material that you want from that little list and assign it to the name input. And that's all you need to do. I copy my material. I need a second one. Make sure you change the index number. And then I select here the material C24. The first material is for my beams. The second one should be for my CLT surfaces. And for surfaces, we have to use the orthotropic 2D, or that's what I want to use at least, the orthotropic 2D material model. So I use a value list to read the options of this material model input and select orthotropic 2D. All right. Now, next step should be the definition of a section. Therefore, we have the section component, yeah, the section for my beams. And again, I assign a name, a number, and I have to assign a material and the name. The material I can link directly from the material component to the section component. This step can only be done if I define the index number first. Because what we expect in this section component is the material index number, yeah, 1, 2, 3, 4, 5. And to transfer it from that component to this one, I have to assign it here first. If I do not assign it, this connection will not work. Yeah. That's why personally I define usually all these index numbers for all my components so I can link them together. Now the last thing is the name. The name is quite easy. Yeah, it's an RM1, yeah, rectangular massive section, and then the width and the height. And I could copy the string and paste it into Grasshopper, or I build it parametrically. The name is just a bunch of strings combined, basically, yeah, text brackets, and the text or the name consists of the part RM1, then a value for the width of my section. And I use here a slider from 0 to 1. I explain it in a second. Then the next part of the name is the slash, and then another slider for the height of the section. All these parts of the name can be joined by a text join component. You just plug it into this input here. And you get the name, or you get one string out of it. Let me show it. Here we are missing the space. Okay, so that's now the name according to RFEM. There is just one little difference. You can see here I'm using, let's say, meters, in my mind, 0.24 meters and not millimeters as it is shown in RFEM. This has following reason. The Grasshopper link is based on our web service, on web service on our API, and this API expects SI units. So I have to define them here, the dimensions of my sections in meters, so that I get the right size in RFEM. Therefore, a scale between 0 to 1. Now I can link it to my name input and the section is done. Last step for this first group here is the member component. Let me show that too. A member component with some basic definition inputs. Under more you can you find options for hinges, eccentricities, nonlinearities or rotations for the member, and under design related inputs. Let's start at the beginning. I need the Grasshopper lines for my members. These 3 lines. Let me rotate the structure. These are the 3 beams, and I already collected them in here. These are the curves, and I connect them to my member component. The section should be this rectangular section, and that's basically it. There's just one thing that I'd want to define in the member, and that's related to the design. I have here timber beams, and I would like to feed already some timber design related settings, so that when I export it to RFEM, I have, let's say, most of the information already defined for the design, and I just have to calculate it. So I have some inputs here, as usually for steel, A aluminum, then T for timber, and for timber I can define the type of the effective length, or the index number of the effective length type, and the index number of the ultimate limit state configuration, or the index number of the service class. I can't define these classes in Grasshopper, but I can define the index number of the existing type. And now you may ask, which existing type? We never defined them. That's where the templates come into play, and I will explain it at the end of this webinar, how it is working. So let me define these types. I used index number 1, and again, more details I will show at the end when I explain templates. So that's already my first part. Let's group it. Materials, sections, and members. Now the second part for my connection to RFEM are surfaces and thicknesses. Let's have a quick look again at RFEM. So a surface consists of some, usually like the main input for a surface is the thickness type, what material and which thickness is defined in here, and it will be assigned to the surface. So let's have a look into the thickness type itself. Here we have different types: uniform, for concrete slabs, uniform thickness type, variable, and also layers. In case of layers, we have a table included where we define each layer, the material, the thickness, and the direction of this layer. Okay, that's what I have to define here, or in Grasshopper. So let's start with the thickness component, which we have here. And the thickness component, again, needs a number or an index number. Then the type, I can use the value list for that. In 99% of the cases, the tooltip will tell you what kind of input it is required. You can see it here, value list. So I connect it, and I can select here layers. In case of layers, I can open the layers tab in this component, and here I have the layers input. The layers will be defined in an additional component. We had to split it up. So in that additional component, I define the material, the thickness, and the direction. This little table that I displayed in RFEM 6, and this information will then be transferred to the thickness component. All right, the material should be material number 2, C24, autotropic material model. The thickness can be defined in a little table. Let's say 0.4, 0.3, again meters, 0.4. And that should be a list. And the same logic for my rotations, the direction of each layer should be 0, 0.5 multiplied by p, 90 degree, and 0 again. Okay. This is this little subtable which I showed in RFEM, and it is connected to the thickness component. We have a lot of additional inputs in here. I can show them as well in RFEM. I do not use them today, but in case you want to apply a stiffness reduction to these CLT thicknesses, then you can activate them with this button, and then you have access to these modification factors and additional options, and all of them are included in our component, as you can see here. So that's the thickness that I want to create. Now I need to connect it to a surface component, and the surface component expects additionally the Grasshopper surface. Now I want to use that thickness type for the roof surfaces. That surface component here, let me show it maybe again, like this, contains all surfaces, again in a tree-like structure. I showed it before, 3 groups. My roof surfaces are in group 1, so what I will do here is I explode the tree that I have here and use, I need it later as well, use the surfaces from the first branch for my surface component. The last step here is the numbering. As I said, I tend to number all my surfaces, so that can be done with the series component. This number, the index number, starts with the value 1. So I define here for the start index number 1. The step is of course 1, 1, 2, 3, 4. And the amount of index numbers that I need, this is linked to the length of this list. I have here 4 surfaces inside, depending how many copies I create in my Grasshopper algorithm. So the length of that list is basically the amount of copies that I need. So I can count the lengths with the list length component and connect it here to the amount of copies. And now I get a list of 4 index numbers, 1, 2, 3, 4. That's what I need for my surface. All right. That's the surface component. And now I need another surface component for my walls. So I simply copy all this stuff. Copy paste. This time I want to use the remaining surfaces. So these are my front surfaces and these are my surfaces from the side, and I connect it as Grasshopper input. Concerning the thickness for the walls, here I would like to use 5 layers, so I simply copy them. Okay, same for the directions. Okay, and I need to change the index number, obviously, of my thickness. That's second thickness, so index number 2. Again, the remaining part is the numbering of those surfaces. I will use a series component again, but I'm not going to start from index number 1 as I did it before. I need basically the last index number from this numbering plus 1. So that's not difficult. The last index is basically, I can read it via a list item component, and I select here the last index, using -1. So I get the value 4 out of this component, and then I add 1 to it, so +1. And now I have here index number 5, which is, parametrically defined depending on the amount of copies and so on. And this is my new start value for the numbering of my walls. The step is again 1, and the amount of copies that I need, or the count, is basically the length of that list. Again, it is not a list, it is a tree structure, as you can see here, but if I flatten it, I have a list, and now I can read again the length. Here it is. The length of that list is again the amount of copies that I need. So I have here the numbering 5 to 10. So that's exactly what I need. 6 values for the numbering, 6 surfaces. That's good. All right. One more thing that I would like to define in here is a mesh refinement. Why? Simply because the default, the global FE mesh length is 0.5 meter. We have here a distance of, what did you define, about 0.3 meters. So let's have at least 3 elements over this length here. So I would like to use a FE mesh for those wall surfaces, or FE mesh length with 0.1 meters. Therefore, we have these mesh refinement components. Here's the surface mesh refinement component. I assign the index number and the required length, 0.1. All right, and I simply connect it to the mesh input. Now, what I forgot also on the surface on top is those are timber surfaces, obviously. And again, I would like to define some things for the design afterwards, the service class and also the ultimate limit state configuration. Therefore, I assign here types number 1 for the ULS configuration, and the same here. Let's extend the design tab, ULS configuration, service class. All right. Again, explanation will follow afterwards. Now, this is the second big group for the connection to RFEM 6. And now the last part, which is related to the line hinges. This is the most tricky part, I would say, in that example. So have a look. Let's have a look inside RFEM, how they are defined. Line hinges, as I said, control the force flow between surfaces. And we find them under types for lines, line hinges. And let's have a look. I have just one type here for all of the surfaces. Come on. And what we can control here is the hinge conditions, which force should be transferred and which not. In my case, I simplified it a bit. I say it's just free about the rotation of the local x-axis. So basically along the line hinge, the rotation about this axis should be free and the rest should be fixed. And then, which is easy to define in Grasshopper, that's not the deal, the issue. The difficult part is this string on the top here. How is it set up? it is set up in a way that we have here the index number of the surface where we want to have a line hinge, and then the related lines. So for surface number 1, lines 2, 3, and 4. For surface number 2, lines 6, 7, and 8, and so on. And this is split by a semicolon and a space bar, and then, you know, the next group of surface and lines comes. So I have to build this string in Grasshopper, and therefore I need the numbers, the index numbers of my surfaces and of my lines where I would like to have a line hinge. So let's have a look again at Rhino and Grasshopper. I do have a numbering for my surfaces. Yeah, I did that here. But the lines where I would like to have a line hinge are not numbered. So let's start here. I assign an index number to my lines. Therefore, I use this line component here. And the line component requires the Grasshopper line and, let's say, the index number that I want to assign to it. The lines for the roof are included in, you know, the roof surfaces. I did it multiple times already. I can deconstruct those surfaces. I get my edges out of them, or I get here the edges of those lines, and I can simply say these edges should be numbered, and the number should be starting with the index 1 until the amount of lines that I have here. So I need a series component. The series component, or the number, should start with index number 1 again, and the amount of copies, this depends again on the list, or the length of this list. Yeah, let me show it quickly. I have here 16 lines, but grouped again. So what I will do is I will make a list out of that group. List lengths. So I want to use this list. However, I flatten this tree to get a list, and the last index, 16, I will use for the count. So I get now the values 1 to 16, and these are my index numbers. Sorry, wrong input. Here, number. I also flatten this input here for the Grasshopper line because I need to combine list and list. Yeah. Otherwise, I will get more lines afterwards. So I have to combine a list with a list. So far so good. All my lines from my roof surfaces have an index number now. And now I somehow need to combine my surface index numbers with my line index numbers. How can I do it? I can do it maybe by collecting the numbers of my surfaces again down here. So this series component, if you remember, contains the 4 index numbers for my roof surfaces. So let me simply bring them down here. So again, I have the same list now here. And let's have a look how the values are shown. I have here the list with the 4 values, and I have here my 16 index numbers for my lines. If I want to group them in a way that I have always surface 1 with related lines, surface 2 with related lines, a tree-like data structure would come in quite handy. So what I can do is I can craft my numbering to a tree. So each index number will be transferred onto its own branch. You can see it here now. Each of these branches from my tree has 1 value. So I have some kind of grouping now. And the same grouping I need for my numbering, yeah, for these numbers. I would like to have for each, or the lines that are related to one surface in one group. I have it already somehow. I have it here. Yeah, each surface has these 4 lines. Yeah, or they are grouped, let's say. And this grouping I would like to assign to my numbering here. How can I do it? I can deconstruct the path. Oh, wrong. Deconstruct path. I can deconstruct the path that I just showed here, yeah, where the lines are grouped. And then I can unflatten a tree from these numbers. And then I trim that tree. Trim tree. And the result will look like this. I have now these numbers, which were in a list before, grouped, and groups similar to my surfaces, as you can see here. Yeah? So now I can combine the first index, or the first branch, the first surface, with the related lines from the numbering. Before I do that, I have to get rid of one of those index numbers, because I want to define a line hinge. Or let's say differently, I do not need a line hinge on the bottom lines. Yeah, I have a line support down here. There's no reason for a line hinge. So I get rid of the index number 0, which is always the bottom line for each group. Easy task, call index. So we remove one index from the list, the index with the number 0. So now only 3 lines will remain here. And how can I build the string that I need for my line hinge now? I can use the text join component a couple of times actually to get the desired result. The first thing that I will do is I need these index numbers, the line numbers, in a split with a comma in a string, not in a list as I have it here. So I join them, and each value should be, is it a comma? I guess. Yeah. Each value should be divided by a comma. So let's see the result of that. Yeah. 2, 3, 4, 6, 7, 8. Okay. Now I can join my surface numbering with the line numbering. So another text join component, for example, where I insert, let me show you again, the surface numbering first, and then second the line numbering. I just have to be careful that I, let's say, use the same amount of, or the same grouping. So I simplify my groups, and now I have here exactly what I need, just not the right division value. I need a space in here, not a space, slash. So index number 1, surface 1, and then the 3 lines in surface 2 and the 3 lines. Similar to what we have in RFEM. Let me show it again. Yeah, surface 1, line 2 to 4. Doesn't matter if we have here 2 to 4 or 2, 3, 4. RFEM will accept our description method, and so on. And now I need it in one long string, or that's my requirement at least. So I will flatten this result and join it by a semicolon and a space. Okay, and now the result looks like this. And this is exactly how it looks in RFEM. So far so good. Now let me use a line hinge component, assign a number to it. assign this string to it that I just created and define the connection. So I would like to fix all forces in each direction and release the rotation. Yeah, you get the information as a tooltip in here. Free, so free rotation is defined by the value 0. Rigid means, or can be defined by inf for infinite, and any other value will be in Newton per meter, yeah, in case of a spring. Okay, that's all regarding the line hinges. By the way, we have also non-linearities for that, yeah, so always check out the more option if you're interested in additional settings. And due to the time, I have to stop here. Basically stop here. I will not continue with the line hinges for my walls, but it is the same logic. You need to number the lines where you would like to have a line hinge. You group it as I did it here, and then you can create this string, assign it to the line hinge component, and you get the line hinges on the desired locations. If you did all that, the next step would be to connect it to an export component. We have it here. That's the export component. Which inputs are required for that? I tend to use a Boolean toggle to run the export. I set it to true if I want to start the export. And if you leave it on true, it's like a live link. Whenever you change something in Grasshopper, it will trigger another export, or you just set it back to false to stop it. The input, that is basically the connection between all our Dlubal components. So each of these Dlubal components have to be connected to the input. Oops. Yeah, I will skip it here because I will switch in a second to my final example, but you can imagine what you have to do here. And then we have some additional options. Flip the z-axis, which I usually use again via Boolean toggle, because the global z-axis in Rhino shows upwards, in RFEM, at least in my case, downwards. So I flip the z coordinates here. What else do we have? We can define the name of the file in RFEM after the export. Yeah, I don't know, example. Yeah, so if I export it in that way, the RFEM file will be named example afterwards. And the last information, or the last feature that I would like to show here, is the use template function. Yeah, I mentioned it a couple of times when I defined my members or surfaces, and it's quite a strong tool, I would say. As you probably noticed, not all of the data that we have in RFEM, all of the objects can be defined in our plugin. We are working on that. Yeah, you saw it in the beginning. We extended a couple of components, we defined new ones, but not everything is included in here already. If there's something missing, then you can't use it, yeah, obviously. But we thought, okay, maybe it would help if you can define a temp, or if you can use a template from RFEM. What's that? Let me go into RFEM quickly. A template is basically a file which already contains specific things. So what you could do, for example, is you could create a new RFEM file. Imagine that's a new RFEM file, and you define some things in there. Maybe some materials, or maybe some sections, or even or you define already the load cases in that file, the load combinations, or add-on related stuff. Yeah, you define here the service class options that, or types that you would like to have, or the ultimate configurations for the timber design. You can define all of that in advance inside RFEM. And not only just that, also the add-ons that you want to use in that template. Yeah, multi-layer surface add-on, timber design add-on. All these settings can be saved inside a template. Save as a template. It's a file that you can put anywhere you want. And then you can link that template to our export. Or you use it in RFEM itself. So when you create a new model in RFEM, and it should not be empty, then you can say, please read the data from my selected template into that new file. And you don't start from scratch. You already have your load cases, combinations, materials, whatever you defined already. And that's the same logic that I use in Grasshopper. When I before I run the export of the data that I defined here, I can read the information from a template. And I can link this template via the path. So I go into my Windows Explorer. Now I have to remember where I put it. I think it's under the programs, Dlubal, RFEM 602, models, RFEM 602, models here. Example, I think company templates, and here's my template CLT1. So I copy the path, put it in a panel, add the CLT1 FT6. FT6 is the ending for templates of RFEM 6, and I link it to my template input. And now when I run the export, it will read first the information from the template and then the information that I defined in my components. And since it reads the information from the template first, and I defined already a timber class in that template and a configuration for the timber design, I can assign, or I can simply use the index number of that type and assign it to my surface, to my member, whatsoever. So yeah, I don't have to define it in Grasshopper, but I can use it from the template. Yeah, so far so good. Let me show the final. Oh no, that's not the final. The final algorithm. We did all that here, and a part of the last group. Yeah, these two definitions are missing due to the time. I think it's anyway clear how I did that. And now we can run the export. And I would like to show that at least once. So let me put it on the right hand side. I close that file. And now, yeah, that's the path to the template. And now I can change it to true. And we should get the file in RFEM. Yeah, it's creating a connection with RFEM. Reading the data from the template. You can see it already here. Load cases and so on are defined. That's part of my template. And then it will create material sections and so on based on the Grasshopper algorithm. All right. I disconnect the connection and I can see my file here. I have the geometry that I expected, my surfaces with the openings, my thicknesses with these layers that I defined before. Yeah. And yeah, that's already a file I can calculate. Let me maximize it for a second. I can generate the mesh. In this predefined algorithm, I used the mesh refinement of 0.2 meters. That's why I have just 2 elements and not 3 over the width. But you can clearly see that the mesh refinement has been defined on these walls, yeah, except to the roof where I have the global FE mesh settings. And we can also see that I have here these line hinges defined, and yeah, all the things that I showed here. And if everything is fine, we can also run a calculation and we can get the results. And this step, running the calculation, can also be triggered via the Grasshopper component. Yeah, so that's also possible. All right. That should be it from my side. I hope I was able to show you some new stuff, some helpful workflows, maybe regarding the numbering and the line hinges. And yeah, I thank you for your attention. In case of questions, you know how to contact us. And for the rest of the webinar, I hand it back to Andreas.
Okay, Lucas, thank you for your nice presentation. An additional hint from my side, you can book your free online appointment, such as a product demonstration for RFEM6, RSTAP9, RWind2, our Section 1, or for the add-ons. Just click on that link here, or you can scan the QR code to contact our sales team. Okay, that should be all from my side. Thank you for your attention. Thanks to Lucas for his presentation. Thanks to Paul for the support by answering the questions. I wish all a nice rest of the day. Bye-bye.